Okay, guys, we are starting into Unit 5. Yes, today is 11/18. If that's where you're going with that, as I try and figure out the date.
I don't write the year, I just write.
Okay, so we are investigating another theorem, learning all the ins and outs of the mean value theorem, often abbreviated as MVT. So we already have IVT, now we have MVT. Okay, so we kind of have a discovery part to get us started, and there's 4 graphs, and down at the bottom of the page there are 6 different directions/questions. So draw the secant lines for each of the figures on the given intervals. So the given intervals are between the points, okay? So like on figure 1, the interval here is from 1 to 9. Okay, and we're going to draw a secant line. What's a secant line do? Goes through both points, right? There we go. And we're going to do the same thing on figure 2. When I get to figure 3, I'm going to have 2 secant lines because there are 3 dots. We're not talking about the open dot. I'm talking about the other 2.
How do you know which?
Ooh, that one was a little curvy, but
Straight line across.
there we go. And figure 4. We're going to go with that. Okay, so use the rulers, don't use the rulers. This is why I provided them. As I said, some of you don't care about the rulers, but I know a lot of you do. So, okay, that was step 1, was draw the secant lines. Okay? Now, part of step 2 is to draw tangent lines. So we're going to go in and draw tangent lines, and let me explain, because you'll notice if we look at 2. Are there any points on the graph of each function where the tangent line to the graph appears to be parallel to the secant line you've drawn? Draw a tangent line between the endpoints of the given interval if possible. Let this point of tangency be called x equals c for each figure. So, as we look at figure 1, is there a place I can draw a tangent line that is parallel to my secant line? So it's tangent to this graph at some point, then parallel to the given secant line. I'm seeing some head nods.
At the bottom and the top.
Could we draw 2 here?
Yeah.
Okay. Now, this is where the advantage of the ruler, because you can kind of put your ruler at the 1 and then slide it up or down. That's what I was doing last night, at least. But, so the idea here, I'm trying to remember what values I ended up at. Yeah. Okay. Oof. Okay, something like that, right? With the idea that this middle guy is my secant line, these other 2 are my tangent lines, and I just drew it on the specific part of the graph where it's tangent. I focused more there. It's not that you can't. You can draw as long as you want. Okay. Up here, up top, we're going to obviously have 2 C values here. The C values being where the tangent line touches the graph. Up top, I'm going to call this C1, and it is approximately at 2.5, if you will. Give or take, yours may or may not be exactly there. And down below, I'm going to call this C2, C sub 2. And I know in the notes they use 7.2. It's more than 7, less than 7.5. Maybe your graph looks slightly different. Honestly, it's not a huge issue. We're just trying to get the approximate values. Okay. Ready for figure 2? Figure 2. Thoughts? What? No? Yeah. The only place we could maybe consider it would be up here, but that is a cusp, sharp point, and we can't draw a cusp, sharp point, anything, we can't draw the tangent at that situation. So in figure 2, there's none because it's not possible there. Okay. That cusp, remember, is a non-differentiable point. And I think, yeah, we'll talk about continuous and differentiable later. So, okay, figure 3. We have a secant line and a secant line. Thoughts on tangent lines?
Yes.
Yes? Is there one on the left portion here?
Yes.
Something like that? Where?
We're going the same thing that way to be parallel to the other.
You would want it on the same piece of the graph. So like since this tangent line goes from 1 to 5, this secant line goes from 1 to 5, our tangent line needs to be within that same interval.
And so the same with the other one.
And so then, yeah, right here we have an interval from 5 to 10, and so with that secant line, then a tangent line in that segment. Okay? Did I end up parallel there? Close enough. Okay. So those two are my, let's see, tangent lines. We have a tangency on the first one at about 3, give or take. So C sub 1 is 3. And on the next one, it is approximately 6. So C sub 2 is 6. If yours is not exactly those values, it's good enough. There's only so much you can do here, right?
Your line's gone.
Where'd it go?
Bishop on your shoe.
I had a secant line here, yes?
See?
Gosh darn it. Okay. Well, think about the whole tangent question while I redraw my secant line. I must have hit a back arrow and messed it up.
Like, how could you have hit the back arrow? That was the last thing.
Well, I think I had to have hit the back arrow right after we did it. Like when I went over to the next page of directions and came back, I probably hit the back arrow, the undo arrow, instead of going back a page and didn't even realize it. Until I go to draw parallel to my secant and it's not there. Okay. Can I draw parallel to this secant? It's going to be kind of close, but there's a spot there, yes? Because again, we're only on that interval from 1 to 5, right? That's the interval we're focused on. And there is one that is slightly above it. Yeah, I'm just going to leave it. Officially in my notes, I have that it happens at about 4. I don't feel like mine really looks exactly like 4. I feel like mine looks more like 3.5-ish. So, but this is our tangent line. And honestly, we don't even use these numbers for anything, do we? So if yours looks 3.5, you could use that if you want. I don't even think that's exactly 3.5, but but that is my C value there. Got them? Now we're going to go answer some questions about them. Okay. For each figure, estimate the value of x equals c where the tangent line is parallel to the secant line, or explain why it is not possible. We're just going to go through. We've pretty much already done this, haven't we? Because we pretty much, as I went through, we kind of talked about it and listed them. But on figure 1, what were my c values there? We had 2, if I recall correctly. We had points of tangency at approximately 2.5 and 7.2. Okay. What about figure 2? There were none? Why not? Okay. There was none, and the reason because there was a cusp. What about 3? Okay, 3 and 6. And on figure 4? Is that the one I said I put minus 3.5? As I said, my notes say 4, but the way I drew it, it looked like 3.5. So if I was drawing on paper, I could go with 4, but there's a little bit more error on the bid queue. So I know when anytime I looked at this portion of the video because I was trying to figure out exactly what what the intention was of these notes. Which is that's when I go and look at the videos is when I can't figure out what the intention of the notes are at that point. I go and watch the video. And with this one, she's using your smartboard to do it, and it's, so it's computerized drawing it. And so she will pre-draw the lines in, so where she can just have a line like if you're in Word or something, and then just drag it up to where it needs to be. So she has it pre-drawn in ahead of time, so she's not doing that on the video, which is interesting. But yeah, thus thought about pre-drawing my lines in, but
Doesn't make it as special.
yeah, see. Okay. 4. Which functions are continuous on the given intervals? So the given intervals being from beginning point to end point. Which ones are continuous? And we talk about these. I don't know if you caught, yes, they're figures 1, 2, 3, and 4, but it's also f of x, g of x, h of x, and k of x. Okay, each graph was labeled. Which ones are continuous? F of x continues from 1 to 9. What? G. Continuous, yes. 2 to 7. Can I draw that without picking my pencil up? That's kind of what I think of with continuous. What else? K of x. Again, I can draw that without picking up my pencil. No to h of x. Okay. Oops, wrong way. So which ones do we, F, G, and K? So F of x, G of x, and K of x. Question 5. Which of the graphs are differentiable? Okay. F, it's a nice smooth curve, right? So F is differentiable. And keep in mind, we're talking about on the given segment, right? And so that one, we were only concerned from 1 to 9. G, we're talking from 2 to 7. Is this differentiable? No, because of the cusp. Okay. H, we're on the interval from 1 to 10. Is that differentiable from 1 to 10? No, because there's a, well, it wasn't even continuous to begin with, was it? Okay. So it's not continuous, it's not going to be differentiable, but there's a jump there, right? Okay, what about K? What's my interval? 1 to 5. Is that differentiable in the interval 1 to 5? It is. Okay, it is from 1 to 5. Now, if we go past 5, it's a no-go. But from 1 to 5, it is. Yes?
On h of x, it's broken up into two different.
But we're looking at the
Whole big.
whole big interval.
Okay.
Does that make sense?
Yeah.
I'm just looking at the whole big interval. So differentiable was f of x and k of x. Oh, I forgot what question 6 was. Which are not differentiable. Explain why. So g of x, y. Okay. So g of x has a cusp at x equals 5. What about h of x? Okay, it's not continuous at x equals 5. There is a jump discontinuity. Okay. Okay, continuing along. This takes us to our topic of the day, mean value theorem. Now, we're going to go through it here, talk about it in words and all that, and then we will get to some examples and, look at how it fills out or, follows examples. So, if f is continuous on the closed interval a to b and differentiable on the open interval a to b. Now, did you catch the subtle difference between the intervals there? If it's continuous on the closed interval, which involves the endpoints, and differentiable on the open interval, which does not include the endpoints. So beware of that. When we're talking about if mean value theorem, MVT applies, that's one thing you have to consider. Then it says there exists, so this is one of our existence theorems, a number C in the interval a to b, so C is between a and b, such that f prime of C is equal to f of b minus f of a over b minus a. Perfectly clear, right? Now, when we talk about this, when we do f of b minus f of a over b minus a, and I don't know why a is not here, but this is the idea of this is a, this is b, and this is c, so to speak, right? I guess it's more the interval, not exactly those points, but with that in mind, when we talk about f of b minus f of a over b minus a, that represents the slope of the secant line. What is f prime of c? Derivative of the tangent line, right? So this is the idea, is saying the slope of the tangent line is equal to the slope of the secant line. I know that's one of the things I wrote in my notes. Slope of tangent line is equal to slope of secant line. So, you know how we were drawing those parallel lines just a few moments ago, right? This is where we are leading up to. Okay? Is that if the graph is continuous and differentiable on that interval, then basically we're saying that there is a way you can draw a secant line, or you can draw a tangent line parallel to the secant line. Because somewhere between those, there has to be a min or a max happening, kind of. Okay? Now, verbally, when we talk about this is saying the instantaneous rate of change equals the average rate of change. Or if you want to go back to, was that Unit 1, Unit 2? This is saying that IROC is equivalent to AROC. Remember that? Okay, so instantaneous rate of change, which is your f prime of c, is equal to average rate of change, which is your slope of the secant line. Graphically, tangent line is parallel to the secant line. And so you could think of it as f prime of c, which is that derivative line, is parallel. You guys familiar with the parallel being the two bars? Kind of like perpendicular is the upside down t. This represents parallel. But it's saying that f of parallel to f of b minus f of a over b minus a. So those are some things to consider. We will, in some of our examples, we'll look at this and say, okay, they'll give us a function interval, and we have to decide if mean value theorem would apply. Yes?
Can we go over the requirements for continuity and differentiability?
Okay. Continuity, if something is continuous, there's no, I'm trying to think how I want to mention this. There's no discontinuities, okay? So there's no vertical asymptotes, because that would cause a break of some sort, right? There's no holes. That would cause a break. When we talk about those vertical asymptotes, that could be, I guess vertical asymptote is one thing. What we just saw on the other page, that jump discontinuity, where it just kind of randomly ends and then begins somewhere else at a lower or higher point. My basic definition is, if I can't just draw that graph without picking my pencil up, it's not continuous. Like, that's what I always think of in my brain. So definitely holes and asymptotes are going to avoid that. The jump discontinuities, I don't know if I'm leaving anything else out or not. Okay. Differentiable, a graph that is continuous is differentiable pretty much everywhere except, talks about cusp, sharp points. Is there something else we included in there or not? That wouldn't matter. If something's not differentiable, there's like a hard point usually. It wouldn't be differentiable at like a vertical asymptote or something, but it has to be continuous to be differentiable, right? If you remember, do you remember that statement? Differentiability implies continuity. So if you're told this is differentiable, what do we automatically know without any hesitation? It's continuous. Okay. Does that answer some of the questions there? Okay. Ethan, did I get your question somewhere in there? Or?
Yeah, so just about continuity again. So I know it's a jump discontinuity, but like if it's going and it's got like closed out and then it has a closed out underneath it, and then it continues again. Is that still a jump? Okay.
I thought you were saying, is that still not continuous?
Oh, is it still not continuous?
Yeah, but that's what I thought you were going to say at first, and you just realized that you said, is it a jump discontinuity?
Well, yeah, I know that, but like, I meant to say, is it still continuous or not?
Yeah, anytime, whether it's, so if you're saying like this versus like that, I don't care what kind of endpoints I have there, that's discontinuous. There is a break. It is physically not connected. Okay. Okay. This is mean values there. We're going to apply it here in a little bit. Okay. A sidebar of mean value theorem is Rolle's theorem. It is basically mean value theorem, but a special specific case. Okay, so this is I'm going to say, special case of MVT. Okay, so you'll notice a lot of this is the same in that, or it starts off the same. Let F be continuous on the closed interval and differentiable on the open interval. And then, notice this time it says f of a has to equal f of b. So that's saying our endpoints are equal to each other. Then there exists at least one number c in that interval a to b where the derivative equals 0, where f prime of c equals 0. So when we talk about f of a equals f of b, these are both y values. So this is saying that their y values are the same. I don't know, maybe I should say that's like y1 and y2, so to speak. But so if, when you draw that secant line, my y values are the same, which means I'm drawing what type of secant line? A horizontal secant line. Then there has to exist a place C where there is a horizontal tangent line as well. Okay, so the specific change here is last time it was just there's 2 points f of a and f of b. Now it's saying if those are the same, so if they're on the same horizontal, then that forms a horizontal line, thus the tangent line is horizontal and a horizontal tangent is equal to 0. Okay? If these conditions hold true, there's at least one number between a and b so that the tangent line is horizontal. Okay? So those are the pieces we're looking at there. The idea here that the slope of the secant line is 0 and the slope of the tangent line is 0. Important note, both Rolle's theorem and the MVT, mean value theorem, guarantee at least one value strictly on the open interval, so endpoints not included. What is the difference in conditions between MVT and Rolle's theorem? Well, we kind of just talked about that, right? What's the difference between MVT and Rolle's? With Rolle's, f of a has to equal f of b, right? And so then when f of a equals f of b, we have a secant line with a slope of 0. So overall, you end up with the secant line has a slope of 0. Yes?
So maybe I'm just forgetting about it, but like, would Rolle's work with the cusp?
No, because it says
Like-
differentiable.
Oh.
A cusp is not differentiable.
Yeah, never mind. I don't know what I was like.
That's all right.
Wait, what? What's f of a and f of b?
So A and B are 2 points on a line, or 2 numbers. This is like saying 1 and 5, so to speak. Okay, so then f of A and f of B are these values right here. So this point, that was weird, would be f of B. This point would be f of A. And those points are equal because they're on the same y level. Does that help?
Yes.
I don't know. Tell me what I need to explain here, right? Okay. So what is the difference in conditions between MVT and Rolle's? Rolle's, I don't even know how I was going to say this. Secant line has slope of 0. Okay. What does Rolle's tell you must exist? Strong word there, right? Must. You know, that's always a word to watch for, right? And like true false questions and stuff, right? Must exist on a given interval. Well, what does a tangent line of 0 representing? A min or a max, officially, right? So because a secant line of 0 means the tangent line is 0, then because that slope is 0, there's going to have to be some type of, if I use the word extrema, are we familiar, do we remember that word? Extrema being a min or a max, right? So an extrema, a min or a max, must exist. Extrema, I'll even put it here, min slash max must exist. And that is because slope is 0. That's tying together stuff you already know, right? We will get to the point where we're going to work on applying these some. We'll work on applying them in example 1, but first, example 1, we have to draw the graph. Have fun. All right, I'll meet you in the end. Okay, so use the table of values below to sketch the differentiable continuous function on the grid. Differentiable continuous. I'm going to connect everything, no sharp points, so it should be rounded curves, right? So you guys understand what I want you to do? 0, 1, put a dot. 2, 4, put a dot. You guys are not even looking at me, so I'm just going to keep going and quit reading out loud. Are you being serious or sarcastic? I mean, it was easy for me the last night when I did this. I feel like it's kind of difficult now on the bin Q, but.
That was not sarcastic.
You don't like this?
I'm sure it is. No, I'm sure it is. Was not sarcastic.
Oh, okay.
So really just feeling a bit ruthless today.
Then I'm going to connect my dots. And technically, since those are the ones I gave you, technically you should not go past your endpoints. I don't want to erase my whole curve because it's decent, so.
Yeah, what? What am I getting to?
Okay. You guys have your questions on the same page. I'm just going to be flipping back and forth, I guess. I don't know a better way to do this and make the graph so I can actually deal with it. A, find the average rate of change of g of x on the interval 2 to 9. So what am I trying to find here? Average rate of change? Slope of the secant line, right? So the idea that, what did it say? From 2 to 9. So I'm trying to find the slope of that secant line there. And I don't know. Oof. Nope.
No.
Okay, we're going to go with that. It's going to have to be good enough for me. So we're going to be using the point 2, which is 2, 4, and we're going to be using the point 9, which is 9, 11, right? So I'm going to go over to my part A area, and I'm going to try and find my A rock. So in order to find A rock, I'm doing G of 9 minus G of 2 over 9 minus 2. I've already forgotten my, there we go, which is going to be 11 minus 4 over 9 minus 2. Seven over 7, which is 1. Does that look like a 1?
Close enough.
Not bad. I mean, and here's what I'm checking. Okay, does my rise over run look like up 1 over 1, up 1 over 1? I'll take it. I'll take it for a BenQ drawing. Okay. B.
Of course.
Is g prime of 6 equal to the slope of the secant line from part A? So what's the slope of the secant line part A? That was the 1. So I want to know, is g prime of 6 equal to 1? That's what I need to know here. How am I going to find g prime of 6? Slope of the tangent line? Okay. That's kind of what I want to know too. Well, supposedly, if we want to shortcut it, the numbers in the notes used the pair. Well, obviously we're going to use the pair 6, 12 here, right? And then the other pair that they ended up using was 4, 9. Mine did not quite do that. Yeah, I don't think that's going to really quite work with mine.
Mine works.
Does it? Okay. We're going to go with that. And you guys remember when we were doing this previously, this type of piece of the game is an estimate, right? We don't know this exactly. This is an estimate, and that's fine. So this was 6, 12, and this was 4, 9. Now, in all honesty, before I even do the math, can you answer this question without doing any of the math?
Yes.
Because the question was, is g prime 6 equal to the slope of the secant line? Do these lines have the same slope?
Yeah.
No. I mean, that to me, without even doing the math, was obvious. Now, here's the deal. It says justify. So do I need something a little bit more officially than the slope of the lines don't look the same? Technically, we need a little bit more here. So if it was what, f of 6 and f of 4? I think are supposed to be g's. Okay. Pretend those are g's so I don't have to go back and erase. And so then we had 12 minus 9 over 6 minus 4, which is 3 halves. And what do we know about 3 halves? 3 halves does not equal 1. Okay. Does Rolle's theorem apply on the interval 4 to 9? Now, Rolle's theorem. Does it apply on the interval 4, which is right here, to 9, which is right here? Why not? Because for Rolle's theorem, that was the specific one, the slope between those 2 points, the endpoints would have to be 0. And so we can say no, because f of 4 does not equal 9. And thus, the slope of the secant line would not be 0. Now, officially, if you want a little official, f of 9 minus f of 4 over 9 minus 4 would not equal 0. Okay? Those type of justifications on a free response problem are good. We're going to push our way through D real quick because if my BenQ erases over the weekend, I'm not redrawing that. Okay. D. Is there another interval where Rolle's theorem applies? So, are there places where we could have the same endpoints? What do you see? The 4 and the 11 point? And I think there's another set. 11 and 15? Because there's actually 3 in a row there, aren't they? You would do 2 separate intervals. So I have that, yes, Rolle's theorem can be applied on 4 to 11 and 11 to 15, since the secant is 0 on both intervals. And the G is continuous and differentiable also. Okay? So yes, Rolls applies on, and I can say 4 to 11 and 11 to 15, since the slope of the secant line equals 0 on both intervals. You could also say that G of 4 equals G of 11 and G of 11 equals G of 15. Now, officially to apply Rolls, we should also mention that it is continuous and differentiable. Okay? So G is continuous and differentiable on 4 to 11 and 11 to 15. Did I get the basics in? Sorry, that is very sloppy, and I was trying to get you the information quickly. Good news is now I don't have to redraw that previous graph on Monday. I don't think I would anyways, but okay. We have, I guess, like 2 more pages of notes to do on Monday, and we'll go from there.
Are you